In this video, we're going to be looking at pH and the pH scale, and then look at what happens when you dilute an acid or an alkali with water. The term pH is always written with a lowercase p and a capital H. H is the symbol for hydrogen, so that's always written as a capital H, and P just means the power of hydrogen. Now, looking at this table at first, it looks confusing, but let's just simplify things a little bit. Here we've got the concentration of hydrogen ions in a litre of water. And we can simplify these complicated numbers here by simplifying to these numbers here. So this is actually the pH scale that you need to be familiar with. This is the only column that you need to be familiar with here. But if we have a look at what the pH numbers refer to, look at the number of decimal places that this 1 is at. So here there are no decimal places in front of the 1, so pH of 0. Here the 1 is at 1 decimal place, so it's a pH of 1. Here the 1's at 2 decimal places, gives a pH of 2, etc. So as long as you appreciate that the pH number gives us a measure of the concentration of hydrogen ions, that's all you need to remember at the moment. Another thing to notice is that every 1 increase in the pH number gives you a 10-fold decrease in the concentration of hydrogen ions. It's actually a logarithmic scale. So if you go from a pH 1 to pH 2, the concentration of hydrogen ions is decreased by a factor of 10. It's 10 times less concentrated than it was when it was a pH 1. A pH 3 is 100 times less concentrated than a pH of 1. So every 1 increase in the pH number decreases the concentration of hydrogen ions 10 times. The POH scale and the POH numbers, these are just like a reverse to the pH scale. We tend not to focus on these at all because the pH scale it'll tell us the concentration of hydrogen ions, but it also tells us the concentration of hydroxide ions. So these two scales kind of tell you the same thing. So we can pretty much ignore the POH scale at the moment. We've already seen that if you've got an equal concentration of hydrogen ions and hydroxide ions, we call that a neutral solution. So here you can see the concentration, the value here, of hydrogen ions is the same as the concentration of hydroxide ions. These two values are the same. So that would be an example of a neutral solution. Whenever we've got a concentration of hydrogen ions in a solution greater than the concentration of hydroxide ions, we call that an acid or an acidic solution. So if we look at this value here, this is a much greater concentration than this value here. So this would be classed as an acid, a concentrated acid. In a situation where we've got a greater concentration of hydroxide ions compared to hydrogen ions, we call that an alkali or an alkaline solution. So again, down here, you can see the value here for the concentration of hydrogen ions is much less than the concentration value here for hydroxide ions. So this would be a concentrated alkali. So we're going to get rid of this half of the chart at the moment because the pH number will measure the concentration of hydrogen ions, but we can also tell the concentration of hydroxide ions as well. And rather than deal with these complicated looking numbers there, we'll just simplify it down to this number. So you need to appreciate that this is the only scale that you need to remember. You need to know that the pH is a measure of the concentration of hydrogen ions in a solution, and that for every 1 increase in the pH number, there's a decrease in the concentration of hydrogen ions by a factor of 10. So how do we measure the pH of a solution? One method is to use a pH probe. Now, pH probe, it's a simple device that you put into a solution and it'll give you a digital readout of the pH of that solution. It's quite accurate. One downside though is that these are very expensive and they're difficult to calibrate and also quite easy to break. So more commonly in the lab, we'll be using universal indicator. Universal indicator can change color depending on the pH of the solution. So we simply drop a couple of drops of the universal indicator into the solution, we look at what color it goes, and we match that up to this pH scale. Anything that's a green color will be a pH of 7. Sorry, I've just clicked the button. Anything with a green color has a pH of 7, and that would be neutral. Anything that's acidic will go a more sort of yellow into orange into red color. And anything that's alkaline tends to go a sort of more blue to purple color. Now, one of the difficulties with using universal indicator and the pH scale is what one person calls a pH of 10 Somebody else might call a pH of 9, and you might think that's only a difference of 1 there. But remember, for every 1 change in this pH scale is a change in the concentration of hydrogen ions by a factor of 10. So pH 10 is actually 10 times more dilute compared to a pH 9 in terms of concentration of hydrogen ions. So what happens when you dilute an acid and an alkali with water? In a similar way to when you've got orange juice at home and you add water to it, you dilute the orange juice down. We can do the same with acids and alkalis. So imagine we've got an acid here with a pH of 2. The yellow dots here are going to represent the hydrogen ions in that acid. So if we had 10 mils of this acid here, pH 2, and we take 1 milliliter of this, put it in another container, and add 9 mils of water to that original acid, we're going to be diluting it by a factor of 10. And every time we dilute by a factor of 10, we're going to change the pH number by 1. So this is now going to change from a pH 2 to a pH 3, and pH 3 is 10 times more dilute or 10 times less concentrated than something that's a pH of 2. If we take this sample here and we dilute it down by a factor of 10 again, we're now going to move to something that's a pH of 4. Now, pH 4 is 100 times more dilute than the original solution. Remember, you multiply the dilution by a factor of 10 every time. So this is 10 times more dilute than the original solution, 100 times more dilute than the original solution. And moving to a pH of 5, we've now got something that's 1,000 times more dilute or 1,000 times less concentrated than the original solution in terms of the hydrogen ions. And we can do that again to move to a pH of 6. So when you dilute an acid by adding water, you decrease the pH number, bringing it closer to 7. And that decreases the concentration of hydrogen ions in that sample of water. We can do the same with alkalis. So if we started with an alkali of pH 13 and we diluted it down by a factor of 10, we moved the pH from a pH 13 to a pH of 12. Dilute the alkali again by a factor of 10, and you move from pH 12 to pH 11. So as you dilute an alkali, you decrease the concentration of hydroxide ions in solution, and you move the pH number closer to 7. So hopefully by the end of this video now, you'll understand a little bit more about what pH is, which is the measure of the concentration of hydrogen ions in a solution, and you can use the pH scale and universal indicator to get an idea of the concentration of hydrogen ions in a solution. And you should know that when you dilute an acid or an alkali with water, you decrease the concentration of the hydrogen ions in an acid or decrease the concentration of hydroxide ions in an alkali, and you move the pH numbers closer to 7. Every decrease or increase in the pH number on the pH scale changes the concentration of the hydrogen or hydroxide ions by a factor of 10.